Hello, Shivappa ji. Shivappa, shall we start? Good morning, everyone. Shaila madam, good morning.
Good morning, sir.
So today, please ready, we will have one more that extra schedule, extra session, evening session, which was pending on LT Spice. Shivappa, yes, ma'am. Hello. Yeah.
Should we get started?
Yeah. I think we should, and I've given you the access rights also. So I welcome everyone again for today's session. Today we will have again by Shivappa. So we'll be starting now, and then he will give as per his opinion and your consent. We will have a break in between, and then we will have the session up to 1:15, let us say. Then we will have a lunch break, and then again he will continue. But I request Shivappa sir to schedule in such a manner that sessions before 4 o'clock or up to maximum 4 o'clock. Okay, because we will have a pending session of Monday's power cut at 5 to 7 evening. Okay, So
Yeah.
welcome, sir. Welcome, Shivappa, sir, and welcome all. And now stage is yours completely. Thank
Yeah.
you very much.
Thank you. Just a quick recap of what yesterday. Just can you post in chat box on top of your mind what are the things we learned yesterday? Verilog, can you hear me? Is my voice
Yeah, clear. Shivappa, everything clear.
okay? Yeah. Okay. So we learned about different modeling using and various constructs, specifically which are synthesizable constructs and um, constructs which are not synthesizable. Basic data types we went through, and the Verilog program structure, and further full statement, if else, for loop, while loop, and repeat. Those and the operators, Verilog operators available for us to model, and the different data types, nets, variables, we went. And further, case statement, case Z, what are the differences? Function. So we had covered up till this point, and then we did demonstration of a couple of examples in those areas. So now what I do, I design, and then I will come back to this advanced construct after completing combinational and sequential circuits, or in between where required. I'll just refer back to this presentation. A new construct comes up, and then which we will be using in a combinational sequential circuit design. So we have to understand the basic purpose of HCL is for modeling digital circuits. And what are the different types of digital circuits? You have combinational circuits and the sequential circuits. So I'm just starting with an application, and from there we go on. So typically, any design block, right? Any module, if you take, puts and the output, and then in the block you have the design, what logic, what functionality a particular design has to perform. I have taken one simple example of a bus-based UART, universal asynchronous receive and transmit, and APB is a bus protocol. Basically, we were looking at one memory interface, memory which is having read, write, signal, address, and the data. APB, AHB, and AXI, these are all the protocols which gadget, what we are all using. More than 90% of the embedded market is governed by a company called ARM in terms of the processor that we use. Even if you say Samsung is using Qualcomm processor Dragon, inside that you will see ARM Cortex or ARM processor. So now, giving background to this ARM company, and ARM, they standardized certain bus protocols called, this is APB is Advanced Peripheral Bus, and AXI Advanced Extensible Bus, and AHB as well, high performance bus. So it does, if you look at it, is having APB bus. Typically, this will be driven by the processor. Okay, so the system. Basically, if you processor subsystem, if you look at somewhere, I will show you the whole block diagram. So assume that now processor is connected to drive this. What processor does is it configures this block to work in certain way. Okay, and uh, so what this function, what this do, it has to serially receive data on RxD, transmit data on TXD. Okay, and what data it has to serially transmit, now that is coming from the processor. So zoomed in, what would be inside this block? If you look at here, bus translator, whatever processor, now it sends address and W data, write data, read data, and when it is writing, it pulls write is equal to 1. When it is reading, write is equal to 0. Of course, enable, and these are all control signals. Chip select is for selecting this particular block. So now processor comes and for example, what data it wants to send to the serial interface, it puts the data register, it is pushed to the write buffer, and then transmit shift register, and then serially it will send here. Similarly, it will receive serial data on the RxD and then read buffer. Finally, it puts back in the data register, which processor can read, and this data goes through on PR data to processor. So now this is any specific block, design block. If you take, there will be this kind of structure where there is a master, that is processor engine, which is scheduling or controlling or configuring these various blocks to work in certain way, and manages the whole ASIC blocks actually. Now this is write operation and this is read operation. And now here, what would be connected this side? It is, if you look computer, you might have, if you have connected your laptop to a display, you would have connected with a VGA cable. Now this VGA cable, right, will be transferring your presentation or anything to the uh, you know uh, transfer the data or the receive data from the other side. So earlier we were using this UART for debugging serially, sending the data and then debugging the systems. Okay, so nowadays we are using USB itself for debug. Okay. Okay, so before combinational circuits, I'm giving the picture of a particular block design and design microarchitecture, right? From architecture to the microarchitecture, how you proceed with a particular block application. Okay, and now once you're clear with the design, what functionality, what you want to do, now you will have to code RTL for it, right? And I've given little in the background about the register transfer logic, RTL, and it is a flow of digital signals between the hardware registers, which are flip-flops, and you have registers which are sequential and gates which are combinatorial. Okay. So now, if you look at this block, right? So this is combinational circuit, which is having gate. This is sequential, which is register. It's the value. So it is a feedback given. If you look at the output of this circuit, will be a clock divider. Okay. So now, how do you? So now clearly you look at, I need one flip flop, I need a NOT gate. Now what are the inputs and outputs clearly given? Clock is an input, reset is an input, Q is output. So clock, reset, Q. Input, clock and reset, output, Q. Okay. So now here at passage of the clock, now I am modeling this flip flop or reset. If reset is 1, Q is 0, output is 0. Okay, and then else if not reset to Q. This is flip-flop modeling. Okay, and now what about this? Assign D is not of Q. What is this? D is what? Not of output Q. Okay, so now you see use reg here. It is output and also you back internally here. Okay, not of this. So now so you can visualize combination of circuit and the sequential. Okay, so I have a PB design. Anyway, that is maybe towards the end I'll show. Now it will be confusing. Okay. So background of design concept, right? Now we will understand how, see it's a bottom up. Now we will understand how we model this flip-flops, how we model this gates, and then how we build, and then at a higher level we can integrate them. So what is a combinational circuit? So the combinational circuits are the output of the logic, right, depends on the inputs at any point in time, which you have all studied, right? These outputs are depending on the present inputs, and based on the gates what you have used, you will get the output. Now, what are combinational circuit components we use in the digital design? Are gates, simple gates, OR gate, AND gate, all this, decoders, encoders, multiplexers, demultiplexers. Okay. So I need not have to explain all this. Okay. Now, but each of these we will see how we design. Okay. Multiplexers, decoder, encoder. This you have already now, it is familiar to you, this circuit. Decoders, right? These are all combinational circuit examples. So now there are certain gates using which you can construct rest all the gates. Those are called universal gates. Okay, so NAND and NOR are universal gates. So if core companies come to your campus actually, so and all this what I'm talking about is very useful if you're if they are recruiting for VLSI. What are universal gates, right? NAND and NOR. Why they are called? Because all other gates, name it, any AND gate, OR gate, XOR gate, all can be realized using NAND gate and NOR gate. Okay. So this the truth table and truth inputs and outputs. So this anyway these are all clear to you. Let us say this is what may be new to you. See, OR gate using NAND. I said these are universal gates, and I can represent these gates using NAND, right? Name any of these gates can be represented using NAND. How you can do it is, this is how this one NAND gate, I make it as not, right? Because connected both two inputs to X and then both the inputs to Y, and then finally connect to Z actually. So if you look at and analyze the truth table of OR gate, right, when X is 0, 0, right, you see finally Z is 0, right, and then 0, 1 is 1. So like that OR gate using NAND. Similarly, NAND gate using NAND, you can construct this AND gate. So basically now input, finally you are shorting both the inputs here and then connecting. Basically, NAND you are inverting. This is acting as just an inverter, right? Similarly, some examples you can see AND gate using NOR. Okay, and so this is an exercise which you can do. Finally, what is the end goal? If you want to realize AND gate, right? This is your output using NAND or using OR. You look at this truth table, inputs you connect accordingly in order to get the specific output. So now, in order to model the gates, okay, so we use now all the operators you know now, right? NOT gate, and OR, right? This is NAND. So you can directly use. Now assign. Assign is the keyword what we use more for modeling the combinational circuit. So multiplexer, okay. So you're seeing the output and the selection, right? We represent the multiplexer in this way. This is 4:1. You can have 8:1. So when there are 8 inputs, right? How many select lines you need? When there are 8, you need 3 select lines. Okay. Yes, 2. So then you will have here, 8 AND gates, right? So and so that way you can, or you want 2:1 multiplexer, 2 inputs, 1. Then 1 select line is good enough. Like this, you can have different varieties of variants of multiplexer and then construct. So you can use if else. I have already shown 3 ways how you can represent a multiplexer. Okay, and you can use any one of them and then represent multiplexer. So this is using case statement, and this is using if statement, right? The ternary operator, this one which I have already showed you. So now, just like how I said, you can represent all the gates using universal gates. Now, using multiplexer, you can. This is also very important interview point of view. You can realize the gates using multiplexer. Let us say, see, this is a 2:1 multiplexer, right? This is logic design basics. So now, how you can realize this as OR gate? Okay. So now it is up to you how you connect. There is one select line. There are 2 inputs, and you select. You connect accordingly so that you realize OR gate. Okay. So now you can analyze this, right? Let us say 0, 0. A and B are 0, 0. Now this is 0. This is 0. So 0, what happens? Right? Now when it is 0, this will be selected. Now this 0 is passed here. Okay. And next 0, 1. Okay. So basically next is 0, 1. So when when B is 1, it will select this. This 1 is passed to AB. Right? This is how you can analyze. Now A is 1. A is 1 and B is 0. Okay. So now when 0, it selects this. This 1 is passed here. And next is 1, 1. Right? 1, B is 1, A is 1. Okay. So when this is 1, it selects this one, and then this is passed, and then you get 1. So you are realizing an OR gate using multiplexer. So similarly, you can analyze and then make AND gate, NOR gate, NOT gate, XNOR gate, right? XOR gate. So this is a good exercise for you to attempt to improve your logic design skills. Okay. So we have the demultiplexer, the logic circuit designed to switch one common input line to one of the several output lines. Okay. So it is just a reverse of multiplexer. Okay. So you have one input based on the select on which particular line you want to pass this input is what is the demultiplexer does. Okay. And based on the select line, so here 0, 0, A is F, and then when it is 0, 1, B gets F, like this. And the circuit, right, corresponding to this will be this. Okay. So where in general have taken here, application of demultiplexer could be digitally adjusting amplifier gain. All right, you might have seen all these amplifiers with different, even you would have seen this register also mentioned there near those knobs, amplifier knobs, 500, 200. Based on this resistance, right, you are controlling, you are passing this voltage to the output. So the gain is controlled from those knobs, right? So not written the code for demultiplexer, and normally I give this as an assignment. I give, write code for one, and then another one I'll give it as an assignment. So similarly, right? So now you know the truth table, right? And then you know what you want, how the behavior of the demultiplexer is. You can write just like the multiplexer code, what I showed, right? So demux, and then one input, and then four outputs, and select line will be there, all right? So you write this part, and then here or if else statement, and then you will have only one input and the select as a sensitivity list, and then finally based on the select you pass the output. Let us say output four outputs, right? A is equal to F, B is equal to F, C is equal to F, D is equal to F. So like this you can write the code for demultiplexer, the design part. Now we go to the others, which are coders. Coders then converts them to a single encoded output. Okay, so we have 2-bit, 3-bit, 4-bit, right? Depending on the application, you can choose what is the number you want, right? So basically, an n-bit encoder has 2 to the power of n input lines. Okay, so we have commonly used 4 to 2, 8 to 3, right? 16 to 4 line configuration. So some applications can be keyboard, right? So this is 4 to 2 encoder. So basically 2 to the power of 2 inputs and then 2 outputs. Okay, and how it works is, so basically whenever this is active, you're encoding, you're coding that to, let us say, 0 0, right? That's what. So whenever A1 is 1, then you are coding it to 0 1, right? And then when this is 1, so this is how you can represent the encoder. Okay, so in the logic design, right? So based on this you can visualize a circuit diagram for 4 to 2 encoder is like this. So this you study, but I'm just giving the highlights, and also for some of these I'm showing the codes, how you write an encoder and the decoder. So let us say 8 to 3 encoder. 8 inputs, right? 2 to the power of 3, and this 3 outputs. Okay, and of course this works with the enable. Let us say, and the truth table, right? There are 8 inputs. Similar, we analyzed based on these, you are encoded to a binary value, right, to the output, right? So now this one you look at, and then you represent using case statement, right? So when this is 1, output is this, right? The same as is. That's where the hardware, the moment you are very clear with this truth table, and then what outputs and what inputs, how you want to control, the coding is easy. Coding is easy. That's where it has the Verilog, the modeling, hardware modeling should come from the design. Okay, the clarity of design makes the coding easy. Okay, so hope you're following the way how the codes are written. Here enable input 7 down to 0, 8 inputs, 3 outputs, and sensitivity list enable and in, right? In actually it is 8 bits, so that way all are included. Whenever any change happens here, right? So if you observe in all of these circuits what I am talking about, you don't see clock, you don't see reset. So these a part of sequential circuits. In combination circuits, So just the logic design, the output depends on inputs, and then whatever inputs of the map of this encoder, the gate structure is what is involved. Apart from that, there is no clocking. Okay, and the default case also is defined here. And then when if it is not enabled, output you give XX unknown, right? So you can model the encoder like this. Now, if served encoder, what if more than one are active? More than one line is active here. How that has to be managed, right? We cannot expect always an ideal case of one is active at a time. So that led to the use of need of priority encoder. Okay, so there same encoders you can take, and then you assign a priority, right? Input every single time. So then we are confusing this encoders, right? So now what is the solution? We need to assign a priority. Okay? How this works? Based on the priority, let us say this is highest priority when you are giving, right? So you can assign your own priority. Okay, accordingly you can design. So you can assign based on the priority your code and derive an equation based on the priority, and this is the circuit, and show the code for the priority. What happens in priority encoder is, now the moment priority goes from this way, it checks this. If it is 1, it codes to this. It doesn't even bother if in 1 is 1. It doesn't care even if in 7 is 1, right? So priority is this, and then it goes. If priority is this one, right, then it doesn't care any of these lines active, right? So that's how priority encoder works. And if you look at, we use this way of representation where is the same code. If enable, if in 0 is 1, then it goes sequentially in this way order and to 0. Else goes, right? If let us say this is not 1, right? Let us this is not 1 and this is 1, right? It goes to in 1, right? Otherwise it will not. All right. So that is how it the priority encoders work. So you are all using keyboard, and then all this and our keyboard is ASCII code, right? These ASCII codes are mapped to, right, the binary, right, the 7-bit. And if you look at, if you want to represent a specific key, let us say this is representing 2, all right? So this is 0 0 1 0, okay? And then this 2 in the keyboard, if you look at, they're managing by either connecting or opening or closing these this one. So in order to represent this 0, it is here, and this is also 0, and this 1, right, logic 1, right, they are setting here. So this is again logic 0. So set and reset. So the hardware how they manage, just like your hearing this one in order to represent a well. Okay. So like this you can right this different numbers accordingly, and also the ASCII values are coded. This coded this you. So this is an encoder. One more example is this positional encoder. Let us say you have this many directions, right? And all these directions you want to using 3 bits. There are 8 directions and you want to encode using 3 bits, right? So you can do that. Based using the basic the encoder technique. So one more application which you can take, I was and typically any SC, any ASIC, right, would have this kind of structure where you have a processing engine which is connected to a bus bar. This is a bus interconnect, or nowadays they call network of connections, NOC. Okay, and now processor and AHB, this is advanced high performance bus, and let us say from here you have the bridge, AHB to APB bridge, and from APB you have connected to all. For example, now UART example what I have shown can be visualized that it is connected somewhere here. Okay, so just one of the peripheral. Of course, here what will be there? These are inputs and outputs of the chip, right? And so basically, what processor it will be interacting with? Two types of devices: input-output device or memory, right? Your printer is an I/O device, right? Or you can visualize any other some projects. You may do some stepper motor kind of this thing directly. You connect to the I/O, right? So those are all I/O systems and the memory subsystem. So now here, why I brought up that our processor need to coordinate and configure and then get the schedule the operations, and once they complete the operation they have to inform processor that I have completed. For example, on timer, processor has come and set timer particular operation. Once the time, it has to inform that okay, my counting is done. That is done through interrupt controller. Okay, that is done through interrupt lines. And when there are more interrupt are the connected, say if you look Cortex M0, there are 240 interrupt lines, 240 or 242. So what it means is now that many peripherals interrupt to the interrupt controller. From here, finally, processor may have only 2 interrupt lines, that is, FIQ and IRQ. Okay, priority, and this processor will get the interrupt and by interrupt service routines. Okay, so now so here all these interrupts are encoded. Okay, now how you click this mouse, right, and then the response here, how it is coming? It is through mouse interrupt. Similarly, keyboard, when you press a key, how a key gets the value getting displayed through interrupt. Right now, these interrupts are mapped, and this also can be encoded to a specific value here. Okay, these are some of the examples of encoder. Now the decoder. Okay, so I'll complete this combination circuits and then we will work on the lab of the combinational circuit before we switch over to sequential circuit. So because every program, if I just go there, right, and then again coming back and going there, that will happen. And test bench also I need to explain. Now the next part is the decoder. Okay, what is a decoder? It is just the reverse functionality of encoder. Okay, so basically it receives n inputs and and it activates one and only one of it to the power of n outputs. Okay, so basically you have these two inputs. This is 2 to 4 decoder. Okay, and when it is 00, one specific line should be enabled. Yeah. So application of decoder is very interesting and very important to understand. Okay, you all have used memory and memory subsystem, right? So how you are selecting a particular memory chip in order to address, right? That is done through decoding technique, right? Using decoders. Okay. Now let us you have 8K into 8 EEPROM memory. So 8K, how many address lines you need for addressing 8K? A processor, how many address lines you need in order to address 8K? So let me ask, for 1K, how many address lines you need? You can just post your answers in the chat box. That makes it little interactive. Right? 10. Good. So now for 8K, you need 10K 10 address, right? So for 10K means that is 1K. For to answer that as immediate answer will be 20, right? Actually, now 2K means just one more address line is. So now you have this memory in the binary, right? This you have 0 to 1023 locations. Okay. Now how many address lines? You said 10 address lines. That is A9 to A0. Okay. Now in order to get this is 1K. Okay. So in order to get 2K, how many address lines? In order to 2K, all that I need to do is A10. A10. What happens here? When A10 is 0, this is selected. When A10 is 1, you get one more here, where 0 to 1023, and then from 1024 to 2048. That is 2047 is the last location here. Okay. So that is how now this is 10 address line, 11 address line, and then for 2K it is 11, for 4K 12, for 8K it is 13. So that is A0 to A13. Okay. Now processor, right? Let us connect this to the processor. How do we connect to the processor? Processor address bus is shared to all the peripherals, all memory or IO peripherals. Data in is also shared. Data, because processor is driving to all, right? Now data out is coming from each one of these, right? Now data in is common, data out coming from each of these, right? And this will be passed to the processor based on the selection, based on which chip is active, right? The finally I want to select this chip. Now what is the address range of this, right? Address range processor, now in the whole address map, let us say 32-bit address processor has 32-bit address. Now in order to address, for example, now 8K memory, one chip, right? You need 13 address lines, right? And okay, I have 8 chips, 8 memories. And now in order to address these 8, how many address lines required in order to decode? We have used 3 to 8 decoder. Okay, so 3 to 8 decoder, and just like how I was extending that A9, A10 like that, A12. Now I go for higher order address lines, that is A13, 14, 15. These 4 address lines, these 3 address lines I use. use in order to get 0, right? Then this one is selected, right? And that is sorry, let us come from this side, right? This one, and then when this is 2, this is 4, this is 6, right? So you can, this is the real application of the decoder actually. Hope you understand this. Some of you know you're answering well, and if any doubt, you can ask me. Very important concept actually. So I've just taken what really to be understood and known by any engineer who's coming for VLSI. Many things you study, right? And good. With that base, what we normally use highlights of these. Coming, and these address lines you pass to decoder and then select. Can you select all at one go? No, you have to select one at a time based on the that is the processor job, right? In order to schedule one at a time. Okay. So basically, in order to generate chip select for the peripherals, we use the decoder. So simple decoder, the same way how I'm showing the code, right? Based on this one, right? You just write this, represent this truth table, right? So that is about multiplexer, demultiplexer, encoder. So now one another very important, combinatorial circuit what we study is adder, right? Simple adder to represent the sum and the carry and the truth table, and this is full adder, right? You can use 2 half adders and then construct the full adder, right? So in all the philosophy or the principle, the approach what I am taking is first this, and then after you get into the so now simple. Once it is clear, you know how to write code in Verilog for an XOR gate or an AND gate or OR gate or anything else, right? So this is off adder. Okay. You used the 2 off adders and you have connected and make a full adder, right? And there's a truth table. Now, just about instantiation. Now, we instantiated one design in the test bench. Now, here, I mean, what is already available in the previous slide. This I am instantiating in order to make a full adder. So now, if you look at these input outputs are input outputs of full adder. C in AB, SC, right? These are the inputs and the outputs at this full adder level. Now, I have taken 2 instances. So, for example, now A, B, both are primary inputs, and now sum, right? The sum is intermediate output. This sum, right? So basically, your is the XOR gate, right? So now A and B, the sum is connected as one input to the next off adder, and carry, that is C temp, it is directly here, okay, to the carry out. So now if you look at S temp is the intermediate sum. This is going as input A, right? And B is getting the C in, okay, carry in, and the sum is output sum, result sum, and then C temp 1, right? It is the carry of the second stage. Now C temp 1 and the C temp, these are producing the carry out. So basically, just I represented full adder using off adder instances. So this is how lower level components can be instantiated in the higher level and then integrate the integrate at the top level. So this is constructing off adder using for constructing full adder using off adder. So this is, if you look at, it is 1 bit, right? Now I go extend it for 4 bit. What do I do? Right? You already have built this full adder. Now this full adder, you connect in certain way so that it forms 4-bit adder. So now this circuit, if you look at, I have instantiated full adder 4 times. Okay, x0, x1, x2, x3 are the instance names. Okay, and now these are specific inputs and outputs of full adder 1 bit, and then you are connecting accordingly. Okay, so now based on how the C out is carried forward, so see the C in is coming here, C out is connected here. Okay, and then this C out is connected to this, and then this C out connected to this, and then final C out is here. Okay, of course these some are S0, S1, S2, S3, right? Okay, and now this A and B, X and Y, X0, Y0, Y1, X1, right? So this is how hierarchically you can build this one, the combinational circuits and half adder and full adder and extending this for 4-bit or 8-bit. So you can do further subtraction, right? Full subtractor, how you represent based on all this. The base is this. You know the logic. Now D you want to represent just like Boolean algebra. I have not. We teach Boolean algebra and basics of all those in general, but we have skipped here, looking at the time. So now all that what we do, you're simplifying, right? You're simplifying the gate structure for the optimal gate, this one, and then you are representing, right? So that once this is clear, then writing the code, right? Module. And the multiplication, right? So you can always look at a simple way of multiplying things, and then how you can represent using, finally, you represent the multiplication, right? Using adders, right? So in same way, now once this gate structure is available here also, right? Just represent accordingly, right? I have 2 half adders, and then rest all these assignments. C1 is what, C2, C0 is what, right? A, B are the inputs, right? And then here I'm also giving the inputs, and in order to see whether the multiplication product is okay or not, right? So at 1 nanosecond, I'm changing the input here. What is the product you can look at, right? This is a simple multiplier implementation. So look at the base, how the things are done. Finally, how you code in Verilog. So you may be thinking that this is very simple, sir, but I'll tell you this is what is required actually. Once you know this, the best of the best design you can produce actually. Okay, and so if you want to represent a 4x4 multiplier gate diagram, right? So and then you can extend it in similar way. You can so that you will see, right? Multipliers are built using adder, right? And this is the structure, and you can extend this, into how many bits you want, the complex multiplier circuits and all. Division, right? So it's a repeated subtraction, right? And then you use the dividend register and this whole thing, right? factor and the comparator, right? And then you represent, and this is one of the code where I'm referring registration for the division. So basically, now this specific thing is done using specific this and computation using some loops and all that. So this you go through. Uh, I leave it to you this part, but I'm saying maybe I'll give this for your analysis, and yeah, it should work
Shivappa,
for yeah.
so, can you give these codes separately so that other whenever they have a time they can practice it? Because chat box getting the code will be difficult afterwards. Can you share or not?
I'll see because all the codes I don't have the intention of sharing because
No,
some of these, yeah, maybe I can
some of
send
these, yeah,
it. I'll
some
do
of
that.
this,
Don't
yeah, some of these like division, etc., multiplication. Division.
yeah, 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 yeah.
Okay,
Do that.
okay, okay.
Yeah. So hope all are following Rathod, especially the code structure, and hope I need not have to explain every line of the code in every slide, and the flow they are able to follow. No, just I'm asking in case if anything I need to explain anywhere, I can spend more time. Not a problem. So looking at the agenda and this thing I am moving, is the pace okay?
Yeah, okay, good.
Yeah. Similarly, we have this magnitude comparators, like digital comparators, how they are built. Right, it's 1-bit comparator. You can write the two table, and then you can represent right the results whether it is greater than or equal, and this one, right? And the same you represent gate diagram, and you want to extend this for 2-bit, right, and the 4-bit, you can do this actually. So basically, you start with right, and then from the comparator circuit, magnitude comparator, and certain are all familiar with, and the BCD code to the display and the circuit. So this also you are just writing the code, especially converter circuits, no clocks, no reset. It is just these inputs, and then you just represent. It's also an encoding technique, right? You are encoding a particular number to value, right? In order to display in certain way, display a number. So that way, it is all your if-else statements actually, or the case statement or the if-else statements, and assign some Verilog what you use. Okay. So we will see some verification part of it. Now the test bench, how do we write? Already just for the multiplexer, I give little background to verification. So in the industry, if you ask me, more than 60 to 70% of the time is spent on verification. That's where if you look at if there are some 5 design engineers, there will be close to, I would say, 15 to 20, 1:4, right? 15 to 20 verification engineers. Even today, what requirements I get is more for verification engineers. And design, one is, right, really we need experts, and also very less number of people can do things. Verification need to be done exhaustively, and it is time consuming because machine time is also involved in addition to our manual effort. That way it's verification takes a lot of time throughout the ASIC cycle. Not only RTL verification, it could be gate verification, it will be physical verification, DFT verification, and the analysis part, the static timing analysis, right, and formal verification, right, and even after the chip comes out, it is still a verification, right? The DFT patterns, your ATE, automatic test equipment, test cases you run, and ATPG you run. After that, you silicon validation, right? So you validate the silicon whether it is functionally okay or not. So that way, industry is involving more people in the verification compared to the design um, and other activities. So, what is verification, right? It is about generating stimulus, applying to the design, and then collecting the outputs and then checking whether they are okay or not, right? That is what we do at the verification stage. So now, you have the design. This design you have instantiated in in the test bench, and in the test bench you declared these signals what you want to drive. For example, finally these, right? And see, this always I'm using this positional positional instantiation. There is one another way I will show somewhere down the line before end of our session. So far order is important. See here, Z, A, B. Z is output, right? It should be connected to here out. So this A, B, C, D, these are input A, B, C, D. You cannot interchange A to B, B to A positionally here. Order is important when you are using positional instantiation. Okay. And now this is the test bench what we demonstrated to you. Okay. And I picked up the verification part separately to give introduction about verification and then construct the test bench for all of this. Okay. So now this is the simulation also yesterday you saw based on the select, the output is receiving the specific input. So typically test bench, we write test bench and also we do, we prepare formal test plan document. See, we prepare a detail just like you prepare your project report for every module. For example, I showed one example APB UART, right? And then we write complete approach. How do we plan verifying, right? Of course, there is a design document also similar to this verification, right? Where they explain what each block does, what are the inputs and the outputs, and the clock, everything they mention, right? And then we give a brief here. We try to put both design and verification in one document. Let us say this is the design APB UART, right? What is the functionality APB, right? About APB protocol, right? And UART is a simple asynchronous serial protocol. Off duplex, what operation it supports, what baud rate it supports, is it off duplex, full duplex? All these features are listed, and all those features listed should be verified, right? This is the block diagram. What we saw, this APB side and then this other side, right? And the state machine of the APB, how it works, and this like this in detail we document how the design works, and on serial port TXD start bit, after that 8-bit and stop bit. So this is the packet structure we use. That's also documented. So is there a parity, right? All this we mention. And later you explain about the signal. Each signal, your address, P-select, P-enable, what are these? You document. Finally, test bench structure. Here it's more of UVM based test bench, but this is your DUT and then this is your test bench task based, which you are writing in order to verify this, right? And the timing, how the APB protocol works. For example, this is first clock idle cycle, this is setup cycle, and then this is access state. How each signal behaves. Just like simple your microprocessor, address data, your ALE, address latch enable whenever you enabling, right? And read write same way. Similar to this, it is a different protocol. This is with wait, right? Basically, when here you see one signal, I'm rushing actually. Not so important at this point, but I'm giving you the glimpse of what industry does, and then see at times, no, I know looking at the time constraint and all, theory is not important, document is not important, right? But without this, we cannot go, and then Verilog languages and tools are just they help actually in order to realize what we want, but otherwise they are dummy, right? Just like your computer. Unless you should know what you want to do with the computer, then computer will be very useful, right? So that way, it's these things are very. Without this understanding, we spend a lot of time. So these you document finally with this protocol.
Hello, hello, Shivappa. I think you are not audible. Am I right? Anybody from Payal madam? Is sir audible? Because I can't hear it.
No, sir. No, sir. No, sir.
No, sir. He's not
Okay.
audible, sir.
Shivappa, Shivappa sir, protocol violation, no communication.
Rathod, sir, I guess screen is also freezed. There is no movement on screen.
Uh, yes, yes. I think we should come back. Oh, you have to call him. Yeah. Okay, please wait. Yes. Hello?
Yeah. Am I audible now?
Yeah, yeah, you are audible.
Skype call came and everything went
That's-
uh,
Okay.
so
Thank God.
okay, sorry about
So,
that.
exactly. No, Shivappa sir.
Yeah,
Shivappa sir.
yeah,
Yeah,
yeah.
exactly. I was about to ask you a question, and it was actually the Skype call, Kiran. Same thing happened. It is related to my question. I'll explain the question. What was my question? Rather
Okay.
than going for such a big APP protocol, because it is good that you have shown, and that gives us a flavor that how exactly the entire
Yeah.
process of verification happens in this entire case study. This kind of a
Yes.
case study,
Yes.
right? Yeah.
Yes. Yes.
But will you also be able to show few demonstrations directly into few examples of like protocol violation? For example, if there's a protocol violation or property violation or any sequence violation, or there
Hmm.
could be some randomization related code, something little small code is also okay, because that will I think give a different flavor that if there's an error, and then how that is being handled. So
Yeah. Yeah.
some little
We can do.
examples.
We say right now whatever demonstration we are
Yeah,
giving.
yeah, that is okay.
So now along with that we can inject some, right, and then we can show you. how
Exactly. That is what is I wanted to ask. You inject some
sure,
errors and then show something. Okay.
definitely, yeah, we'll do that.
Okay, please.
Okay, so in fact, we have Verilog, system Verilog, and UVM case studies to explain. So anyway, we will confine to the Verilog here. See, many times I have received such feedback, uh, especially the teaching community. Once I got a feedback saying that you taught only what you taught is not even up to the extent that what we have in our academics. That was the comment on person gave. He was a lecturer. I am fine, right, to receive. Only thing, all that I ask is just simple decoder. You write a code and then do a test bench and simulate and then share me the waveform, right? That's what today, right? We see that link is missing. That is where we have incorporated all this, and it is all coming from the experience of the industry, and based on that we included all this. And of course, now just like I showed you, I can show this, APB art or AXI memory also looking at the audience, right? So that is where, if you feel that this all can be skipped, I am perfectly fine, and I'll just directly go to even APB art, right? So, but the intent, right? What especially Damodar
Sure.
and then me,
Shivappa,
we have,
Shivappa sir, I'm not
yeah,
telling you to change the flow or skip anything. I'm telling you, along with this, can you demonstrate few examples? Along with this, not
yeah,
skipping.
yeah, yeah,
Along with
yeah,
this,
yeah,
if you can demonstrate few examples like error injection and then how that can happen, will be
sure,
good.
sure,
That's what
sure,
my point was.
yeah, yeah,
Okay.
yeah, yeah.
Okay.
No problem. No, just I'm giving an example where we
Yeah,
see
yeah,
a
please.
challenge actually. Challenge for us,
Yeah.
normally in this when addressing
Okay.
academic crowd, right? So
Correct,
that way.
correct. Okay.
So
No
now,
problem.
yeah. So I put this 3 to 8 decoder. This for the same 3 to 8 decoder. This is the design what we saw. And now, how do we write test bench? Right now, it is all combinatorial circuit. The stimulus when you are giving, right? If you look at, you have instantiated, and then these are these are the signals what you have declared in order to drive and connect to the design. And now here, because it is combinatorial, you need not be always fixing at hash 5. All right, you can give any time, and then you can give even this also. You can put it in for loop or repeat loop, whatever. You can generate as many input variables as you can, and then see how your design behaves, right? So this is the decoder, 3 to 8 decoder part. So here I put the complete thing, and we will see in the simulation also. If you look at enable A and out, right? Enable input is A and then output is out. So this, whenever it is, see, till this point enable is not there. When enable is not there, so output will all be at 0. And then when A input, output, and then when 1, this is selected, 2, this is selected, 3, 4. So this is 3 to 8 decoder simulation output. Okay. So, and we saw the full ladder, right? Full ladder also, you can see how you can basically, you are giving input to inputs and then inside, input carry, and then you are expecting the output, right? This is output carry. And scene, initially you're making it 0 there. And so you're instantiating this, then giving AB, and then making sure your output, right? Output for this. So we simulate all this. Hopefully, you're understanding this code. All that here is the combinatorial. There is nothing this one. So how you write, and also you might have observed everywhere I am using blocking or non-blocking here in the test bench. I am using all. blocking, right? Here, don't want to complicate. In the test bench, what values I want to drive, I am assigning directly to this input, and then that input test, right, is passed to the DUT, and then further the DUT behaves accordingly. Okay, so what divider code I showed, right, and then even for that, if you want to write the test bench with passing a different dividend and divisor and right, you can look at the quotient and the division and all that. So one of the use of parameter, I'll explain. I'll take this opportunity to explain the parameter concept here. Easy. Now here width I have mentioned in the division module as 8. Okay, this dividend, divisor, and the quotient width, right, is controlled by this. Now if I want that to be, now initially 8-bit dividend, right? Now if you want to make this as, let us say 16-bit, right, or even let us say 4-bit, you can control from, from this TB, right, test bench. So now whatever you are giving here, it is passed both here in the test bench and also see here. How to pass a parameter is this. Now you developed a division program, right? And it should support any width, possible width, right? You have a provision to configure this divider, division program to any width, right? So that is the advantage of the parameter. Okay. So some people will ask, no, sir, tick define we have, right? Tick define and tick parameter, what is the difference? Both represent this constant. This is, compile time. This also compile time. Only thing is now tick, define, once it is used here, throughout your program, it is the same value. It is the same value, right? Either this or this. This is per design or per module, you can control the, let us say you have one multiplier, one more, right? There also you may be using some width, right? And you can control that specific multiplier related information there. So this is instance based, right? This is global. Okay, this is global. And one more difference is this is pre-compiler. So this is during compilation, regular program compilation, it happens actually. So those are the two differences between tick define and okay. So that is about this one. All this better we spend some time when. So what we do is now we can take some break. We'll come back and then execute all these programs, then switch over to sequential circuit.
Yeah, fine. When we should come back?
Yeah, this
Evening,
11:20. Yeah, 11:25, right? So 11:25, 11:35, 10 minutes.
Okay.
Okay. Okay. Okay.
Okay. Fine. Fine. Okay. पायल मैडम आप है अभी?
हाँ सर,
वो जो एसटीटीपी के मेल देखे आपने सुबह?
देखे देखे सर, मैं सुबह करने बैठी पर आपने किया था ऑलरेडी रिप्लाई, तो देखा मैंने।
चलेगा, चलेगा, मैंने उनको रिप्लाई कर दिया। मैं देख रहा हूँ कैंडिडेट के वो है इसमें,
है
नेविल और बाकी लोगों के।
है
तो
इसमें
आप
है,
एक काम
नेविल तो
कीजिए, तो
आपका
एक,
स्टूडेंट है सर।
अच्छा
नेविल
अच्छा, मुझे तो भी लगा ही, मुझे तो भी वो लगा वो भी
पृथा
कहाँ
की
काम कर
बैच
रहा
का
है?
है, नेविल पृथा की बैच का
हाँ
है,
हाँ
वो
हाँ हाँ,
इंडस्ट्री
बराबर
है।
है, बराबर है। हाँ सही बात है, अच्छा इंडस्ट्री से हो। हाँ ठीक है, ओके। तो मैडम एक काम कीजिए ना, उसका श्रीकांत को बोल के अकाउंट तुरंत क्रिएट करना पड़ेगा।
हाँ हाँ ठीक है सर।
मैं इसलिए ये बताने के लिए आपको अनम्यूट किया मैं, क्योंकि अभी
हाँ
उसको
हाँ
तुरंत
ठीक है
लगेगा।
सर, ठीक है
आप
सर,
फोन
ठीक
पे बात करो उससे, फोन पे बात करो उससे, श्रीकांत
ओके
से
सर,
फोन पे बात करो।
ठीक
उसको
है
बोलना
सर,
है,
ठीक।
देखो बोलना है नाम है ना, तीन, एक
हाँ
एक
हाँ
मेल में तीन नाम है, एक में एक अलग है, एक में नाम अलग है,
अलग है,
वो भी देख
देखा
लेना।
मैंने, देखा।
हाँ
ठीक है सर।
चलेगा चलेगा, और स्नेहा मैडम को भी वो नाम फॉरवर्ड कर देना।
हाँ हाँ हाँ,
ओके।
ओके सर।
We will resume.
You can resume.
Yeah.
Rathod sir. Hello.
Yes, yes.
सर दिस इज खाड़े सर
हाँ
सवेरे मूडल में कोई प्रॉब्लम था क्या सर?
नहीं, क्यों?
क्योंकि मुझे एक एरर आ रहा था 2 क्वेश्चन के बाद जब मैं नेक्स्ट क्लिक कर रहा था ना
हाँ हाँ।
तो आई वाज गेटिंग अ एरर
क्या किस चीज से क्या आ रहा
रिक्वायर्ड
था?
पैरामीटर वाज मिसिंग मोर इंफॉर्मेशन
अरे
अबाउट दिस एरर रिक्वायर्ड पैरामीटर को
लेकिन कंप्लीट हो गया क्या आपका
नहीं
टेस्ट?
ना,
कंप्लीट
वो
हो
आगे ही
गया?
नहीं जा रहा था। जब भी मैं कंटिन्यू करता था फिर वो बाहर आता था।
ओ
हाँ, फिर से मैं ट्राई करता था, फिर से वही, मतलब 2 क्वेश्चन पे क्लिक करो, नेक्स्ट पे क्लिक करो, सेम एरर।
अच्छा, एनीबडी एल्स हैज
और मैंने उसका
एनकाउंटर्ड दिस एरर?
स्क्रीनशॉट भी निकाल के रखा है।
तो मुझे भेज दीजिए ना, और मैं सिस्टम
ओके
एडमिन से बात करता हूँ अगर टेक्निकल इशू होगा तो। ठीक है।
ओके, तो कैसे भेजूं, मेल पे?
हाँ, मैं तो एक काम करो, मेरा व्हाट्सएप नंबर है आपके पास नहीं है?
नहीं सर, नहीं।
मैं नीचे टाइप कर रहा हूँ, उसमें आप मुझे व्हाट्सएप कर दीजिए।
ओके ओके सर, या थैंक यू।
नहीं, अपना ग्रुप है ना सर, उसमें डाल दो।
शायद मैं नहीं हूँ सर उस ग्रुप में,
अरे ऐसे कैसे हो गए?
पता नहीं, क्योंकि मैं वही सर्च कर रहा था कि सवेरे किसको कांटेक्ट करूँ, क्योंकि मेल पे भी मुझे किसी का नंबर नहीं दिखा।
ऐसे कैसे हुआ?
और आज तो आज
आ,
हड़बड़ी में मैंने लेक्चर भी थोड़ा गैप दिया था। मैंने बोला कल की ले मिस हो गया, तो आज कम से कम अटेंड करूँ।
ठीक है, आप अपना यहाँ पे आप अपना नंबर टाइप कर दीजिए सर, हम उसको ग्रुप में ऐड कर देते हैं, फिर
ओके
आप उस
सर,
पर भेज दीजिए
ओके
तुरंत।
सर,
आप अपना
ओके।
टाइप कर दीजिए। ओके। शिवप्पा सर, प्लीज कंटिन्यू।
या
Yeah, yeah. So we will simulate some of these examples what we discussed, and let us take this decoder 328. Okay. So typically, we yeah. So we write test bench and the design in separate files. Okay. Okay. So now you can look at this is the RTL, the design, all right, and the code what we saw for the 328 decoder, and now this is the test bench, all right, the time scale, and I have included this decoder 38.v, right? Here, okay. Why it is getting stuck in between? Okay. So now the DUT instantiation, and then we are driving some values to the inputs, and I have not put a checker here. So what is the output? And I am not comparing. We will observe in the waveform whether the correct output is coming or not. So this specific thing yesterday, I think Harish explained. In order to dump the waveform, Cadence format is .trn file. Okay, .trn file. This is Cadence native format. Each of these simulator companies, they have their own formats, but all of them, all the simulators will support one standard format, that is VCD, value change dump. Okay, and now how all this, what is this dump is about? It captures the changes which are happening in all the signals at every point in time, right? At any point in time. So that is what information will be here in this database. So that when I load this file in the waveform viewer and it grabs, whatever it has recorded, that would record file record var. Sparse means all the variables are recorded, different values at different times, and those are displayed in the waveform viewer. So this is wait for 100 nanosecond, and then $finish means exit the simulation. And now, as you know, this initial will be concurrent, will be running in parallel. Okay. Of course, when this is running, the design also, right, will be running in parallel. They're always their assigned statements; those also will be concurrent. That's where you can understand the structural and structural design. Okay. So now this part is the test bench, right? So now I simulate here all this. I will clean. No clean. Color run. Okay. So I will remove everything here in the simulation directory. All this previous. Okay. Now it is blank. Okay. Now NC Verilog plus access. Say yesterday yes shown. I will put it in a file, and you can always see automation is a way of doing things. So anything we do repeatedly, we try to automate, right? I will tell you the same thing. I will put it in a file, and then I use the file every time when I want to compile. Okay. So now what is that I want to compile here? One level you go back. Where is my program? Programs decoder, right? What is happening? Okay. Decoder 3 to 8. Okay. .v, right? This is design file. What I do, I directly go for 3 to 8 underscore TB. This is where I have already included the decoder.sv, right? See this, it is showing error. Okay. So what is the error here? Include this one. This program decoder TB cannot open file decoder 38.v. So why it is showing is in the decoder TB, I have not given the path. It is looking, see, whenever you give directly like this, it will look for in the current directory. In the current directory, it is not there, right? So that's what I should say this is, you look for that file in the programs directory. These are all common things which you go through day in and day out, right? So now it has gone through. I think all this structure, all this Harish has explained. And now NC Verilog, it has compiled. And because I have given the dump, it should have created the dump file also. Finally, it has come to line number 29, this $finish after running for 100 nanoseconds. That's our time, 100 nanoseconds plus 0. Now, look at this. What Incalypse is where compilation elaborated database will be available, right? And it has generated dump.trn. When you give this, it generates one more file called DSN also, that is design file. So that is for simulator use. Okay. And history and log. I was talking about yesterday the options. For example, I give -L decoder dot log. So instead of this NC Verilog dot log, now I am asking it to generate a log of my own name, right? I can give -L. That's one of the options, right? So now you see, if you look at now, you would have got one L decoder.log file. Okay, so see this decoder.history. decoder.log, right? And what is there in decoder.log? The recent whatever you saw, right? Those are the messages here. Now you also observed this is shorter one compared to the earlier log file. Can you tell me why? First time when I compiled, see all this came. These messages you don't see now. Why? Because these are all already compiled and then in Incolip's already available here, right? The compiled database. It just touched on that and then it didn't, because I have not changed anything in the design. These are all the basic things, right? So you should know. So that is where only incremental compilation it did. There was nothing to compile. Let us say I changed some file names here, right? Let us say this file has changed. Okay, I add one more this one, right? And now this is changed. Now you see it will compile the whole thing. See, are you seeing? Because the source file changed, again it compiled, and then you see all the messages. Okay, so now that is about this compilation and simulation. It is simulated also. See this run, and it is simulated 100 nanoseconds. Now dump.trn. We use SimVision in Cadence. See, typically this is the practice. We don't run GUI mode. That NC launch, it is available. You can open NC launch and there you compile, right? There you can simulate. Just like whatever run, exit, all this I have given, you can give in NC launch, right? So typically we don't follow that. That is for two reasons. One is efficient use of simulators, right? And also, when you create the database offline, anytime you can debug. So how it is efficiently used? EDA tools are very expensive. How it is used is, for example, now am I holding any license for license of this NCSIM now? No, because only during my compilation and simulation I use. Now I am not using anything, right? And when you open the GUI NC launch, right, you will be holding the license, right? Now you are holding the license. So there are ways to check actually if they have enabled that also. You can check here LMA if it allows. Okay, lmstat minus a, it allows. See this, it lists what are the licenses available and which one you are using here, right? So for example, this floating license, right, this is currently used. If you look at total 51 licenses are issued, one license is in use, right? Okay, and similarly what you saw, all this test spectrum. So all this is the way we check the license utilization. So now from NC launch, you can compile here. It's all GUI. Okay, you go and then file. You just STF compiler utilities. One afternoon, Harish will demonstrate one GUI mode also. Now let us not take out that branch now. We will see. So you can do the GUI also, but I'm suggesting you, GUI is not the industrial practice. Okay. So now I will open the waveform viewer. I said SimVision is the one which we use for waveform viewing um, in Cadence. So Okay, so now this monitor resolution is better. So file, open database. Now this dump.trn is the one which is created here. Okay, and then select that. When you select that, you see this dump decoder 328 TB, right? And under that, UNOT. This is the instance name, right? If you look at what is the instance name you have used PPT, are you seeing this? U0, right? That is the instance name. What you will see with the hierarchy. This is design. This is the test bench. Now, in the test bench, what are the signals you have declared? A, enable, out. These are test bench signals. In U, these are DUT signals. So basically, these are the ones which are driven to the design. Okay, so that's where you see what value you saw here, the same is applied to A, right? And then what value, for other signals as well, right? You see here. So, okay, so this is how you can take and then analyze. Of course, zoom in, zoom out, all these are there here. You can play around with the GUI, okay, and any other things, right? You can apply grade and all that you can do, and you can search a signal, and you can. One more is any changes happening on a particular signal. You select a signal, and then you click this. Where change is happening, it will show, right? So all this will be handy, and then you can search a signal. You can search for a value. Let us say 40, right? It should take you to the place where this value is 40. Let me see. Yeah. See this? So this, it's all GUI. You go and then explore, and it displays what signals are there in each scope, right? So this bare minimum info is good enough for you at this point in time. And then further you can. So even I think it supports Radix. Right click and you will get a lot of these options. Trace driver in sidebar and all that with signals driving. Send to design browser. This source browser. You can see the source also. You can open the source, right? What not? A schematic tracer. The schematic, right? So at a block level, not at a gate level. You will not be able to see at a gate level. So gate level you have to synthesize. And what else is there here? Yeah. So you can save the signals. See this set of signals you have taken. File, save command script. Okay. Next time, this you can reopen this set of signals. How you can do that? Let us say close database. Okay. So it's closed. Okay. Now I closed. Now next time when you open database, now I open database. Okay. Now I don't drag the signals. I directly earlier saved signals I will take. How you can do is source commands. So last time what file I saved? Dot simulation. Oh, no, I didn't give the file name. Sorry. I'll show you now. This one file save commands, save to file. Okay, so decoder. Sorry. Wait, I'll give some name. Yeah, decoder dot svcf is what it should save. Now, if you look at now I close. Again, I'll open. You can as well see in this hanging. Let me. remote server connection. I should have. 1 minute. Let me connect. Lost the connection. 1 minute. Now, here you can go open database. Now, source command script. Now you see decoder SVCF what I saved. See, now those signals. See, because every time in a complex design, there will be too many signals you have selected and then ordered for your debugging, right? And specific inputs and outputs. And every time you don't want to keep dragging the signals and then waste time. So that's where this will be very handy. Only the signal set it will file, not the whole database. So database will be saved in, the changes are saved in which file? .trn. Okay. We'll still keep this window usage, right? SVCM, this SimVision. Okay. Okay. So now we will see other examples.
Hello, sir.
Yeah. Yeah.
Hello. Yeah. Is it possible to see the internal signals of the design for the debugging purpose using a waveform analyzer?
Yeah. Very much. That's why I opened the browser. This is the design, right? Now this is the design. Now let us say I will say source browser. Send to source browser. You have the source here. Now your internal signal here basically all happens to be either in the input or the output, right? These signals, right? Now let us say this decoder TB. If you look at
I'm talking about the internal signals, sir. For example, for 4-bit carry propagate adder. Yeah.
I am coming to your point. That's where I took it. Now see what is internal for your understanding. Now whatever is there in the port, they are external signals or the interface signals. What you are declaring inside the module, these are internal signals, correct?
Correct.
Now that's where in the decoder design, all were inputs and outputs. I took this test bench where these are all internal signals. Now you take this enable and drag. This is the enable, right? And so that way you can go to any hierarchy and then pick the signal, internal signals, and then you can display. It will allow. It should allow. That is how you can debug, right? Otherwise, only at the interface signal, how do you analyze, right?
Yes. Correct.
I will show with some off-adder example. That way it will be more clear because it will be having multiple hierarchies, right?
Okay. Thank you, sir. Thank you.
Okay. So now this is what we saw. We will see multiplexer should decoder, and let us see full adder and then full adder. So what is there in full adder? Anyway, right? Right, the same code what I right, the full adder code, and created the off adder. See, I've written off adder module here itself, and this off adder in the full adder I have instantiated two off adders, and finally now if you look at these are inputs and outputs. Let us say this S temp, C temp, and C temp one signals for you, right? Here we can look at actually. So now full adder, full adder, full adder TB.
E-
Yeah, getting hanged quite often. Yeah. So now this is the full adder test bench. So I have in the design file here, and now these are the signals at the test bench level, and design is instantiated. And then these are the inputs what I am giving using 1-bit full adder, right? And then there is record var, right? So you can as well use, because all initial are parallel. For example, if you see dumping I have used here, and then here dollar finish, right, I have used in this initial. It's all fine actually. Otherwise, you can as well use this dollar finish 100 or whatever here. It's all fine. So there is no specific this thing. You can. Okay. So now that is the full adder part. Now what I do, I will remove all the decoder part. All this is all simultaneously created. I need not have to save it. That's one more thing. I design my test bench. It could be taken to any simulator, and then we should be able to simulate. Need not be only this. If I use VCS command, I should be able to compile the same using VCS, right? So it is not tool dependent. Verilog files are not tool dependent. Okay. So now what I do this time, create on simple run.sh where I put this command. What is my command? nc verilog plus access plus, okay, and now what is that? That is full adder. Full adder tb dot v. You can as well give -l add. So now this, instead of typing every time this in the command line, I can execute this file. Okay. So now you save this and see all plus access or -l this. Okay, this one should do. Now, if I directly say run.sh, see it says permission denied. Now I need to give, by default, if you look at any file you create, see it is only read write permission here, no execute permission. So that way I give execute permission plus x means execute permission to run dot. So now if you look at this file, you see this one x is given. Okay, and now I run this. Cannot find privileged file full adder tb dot s. Yeah.
You have to go back.
Yeah, exactly. Right. So this run.sh. And normally,
Dash.
see what happens. Normally, we keep this GVim or editor, keep it open, and we do all those changes there. Okay, only use command line. All this we do. Here, the gedit, the fonts are small. That's where we have to live with it. Okay, programs, uh, right? In that. Okay, so now it is and simulated, right? And then so now if simulation, close this, and file, open database. Okay, go now what is there? Let us see. Oh, directly it came full adder TB directly. It has picked up full adder, and see this hierarchy of it is showing full adder TB. Under that, full adder the inside test bench full adder. This is the design top. Under that, off adder instance 1, off adder instance 2. Right? Now, if you look at here, this off adder instance, when you select, right, ABCS is what you are seeing. You can also filter out here, okay, hide unprobed and hide assertions, show and transaction, this one, internal. See this? Okay, hide this one. It is not showing. This is also one more way. Inputs, outputs only you block. Only inputs, only outputs. You can select here. Okay. However, in case you drag this, now you are seeing this input and output. So if you go to source browser, the input and output assign. These are the things which are there in off adder, right? And full adder is where you should go. Let us say this instance. See this? Now, for all the internals, these are input outputs. Let me try internals. What should happen? See this? This hide internals is this one. Now, okay, only inputs, outputs, in-outs, and this internals. Okay, internal signals are the C temp and all that. Okay.
Okay.
So this is off adder thing, and then this is full adder instance. Okay, all this.
Yes.
And this bit carry for a specific input how off adder works, and you can add divider here. Something called divider is there. What is that? Create divider. Let us say that one you name it as off adder. Okay, yes, put the divider there. So now this one you create a divider. Okay, so now name a divider. Yeah. So like you can debug the designs actually. So now this is off adder stuff, and for A, B, carry, and then sum, and then this is the full adder stuff and this internal signal. So that is about these two designs. I think others you can do in similar way. You can simulate, you can write simple test benches and then try out. Okay. So completes combinatorial circuits. Okay. Combinatorial circuits. Now we will move on to the sequential circuits. There we have interesting things. Okay.
काय आवाज येतोय?
पाऊस
बापरे.
केव्हापासून स्टार्ट आहे हे थांबतच नाही आणि असंच पडते.
So and so far discuss things. Any doubt before I move on to this?
Sir, before going, can you once again explain the architecture of interface between 8-bit processor and RAM of 1 KB? Just the architecture. You had that in the previous lecture. That is extension of address lines for using decoder.
Yeah,
or
I got it.
accessing the RAM positions.
Is this?
Yeah.
Yeah. Okay. Okay. What is the doubt here? Just 1 minute.
Regarding only A9 onwards file address lines.
Okay. 1 minute.
That is A9, 10, 11 can be done. But what about 12, 13, 14 and the same RAM position by some other data will get corrupted. The RAM location is the same.
1 minute.
So you have to write and read and then only write what type of sequence you use, then it is okay. But if you have some RAM, you may not be able to write 2 into 16. Isn't it? That's my doubt.
Yes. Yeah, surely. I'll just clarify that. See, if you sorry. Okay. So no problem. I'll just share this part. Share the other window. The part we are discussing. So now, wait, I just switch to other monitor. That's a little bit confusion. Which PPT is coming where? Okay, this is yeah. Yeah, this part is very important. At any point in time, right? At any point in processor can address only one of the peripherals. Correct? Are clear
Yes,
with that concept?
Yes. That is true.
Let us say, yeah. So this is RAM. It is reading, right? Is the slide okay? Are you able to see the screen?
Yes.
Okay. So now this is the read-only memory. It reads, and then basically it is used for skipping program, boot RAM. When you bring up a device, right? You use RAM. Now next is RAM, which is read, right? So processor can come and write and at the same time read. And here, this through this bus bar, that's where I said knock. So it can also access. Now for this, this is one of the peripheral, right? It will give us 1, 2, 3, right? Now for underneath, there could be 16 peripherals which are connected to APB. This is APB bridge. See, this is a bus translator. AHB is the interface here, okay, and then this is APB. So now it translates AHB, all the transactions coming from processor in the form of AHB using this bridge to APB. Okay, this is one point. Second is, now in order to access these peripherals, let us say now 16 address lines are reserved. 16.
Yes.
That is total 4 of 16. So this is 64K memory is what? 64K memory is stored or mapped, right? It's all memory map. You know this IO mapped, IO and memory mapped, right? And memory mapped.
Okay.
Memory map.
Okay, sir. I got it. I missed this point.
Right? Okay. Now, this memory mapped. Now, further, this is the same address space is shared by 16 peripherals. Correct?
Yes.
At 6, our decoder example understanding, this is shared by 8 peripherals. Okay? 8 peripherals. Now, I come to that decoder example here. Now, these 8 peripherals are these. Okay? All, let us say they are all memories. And 8 peripherals, 8 memories, each of size 8K. And right hand side 8 is data bus.
Yes.
We also say this, it is width of the data bus. Now, this one of these, any one of these.
Correct.
How do you select? Is coming from the decoder. Now, all of them, in order to address 8K memory, you need anyway 13 address lines. This you are not disturbing. Correct? The last location is this. If you write in nibbles, FF, right? Here itself we can see this one FF, right?
Memory map.
When this is 0, 0, 1. 0, 1.
Yes.
Is this clear? This is how I decode. Now,
Yes, sir.
sir, you're showing this. Now, how this is translated here is like this. When it is 0, 0, 0, this one. When it is 0, 0, 1, this one. Right? When it is 0, 1, 0. And this is the, now 2, 4, 6, 8, all that what you are seeing is coming from these address lines. So, look at this, what address. So this is A12 and so A15. 19 001002. So you shift this. Yeah. This complete column. Right? So
Yeah, I got it, sir. The lower
024.
13-bit address
Okay.
is.
Exactly.
Mm.
Now that is how the processor. Now, what question conflict you are
No,
saying, right? That question is what? Tell me, Ellen.
no, sir, the architecture is clear now. The lower 13 bits are coming from the processor, while the
Lower 13.
higher 3 bits are coming from 3 to 8 decoder to access any of the EPROMs at a given instant of time.
Yes. Yes.
Yes, so
Exactly.
it
Yeah.
is clear. It's clear, sir.
That
It
is
is
that.
clear. So there are
Okay.
8 different peripherals and one can be accessed at a time.
Exactly.
Yes, yes.
Yeah.
Okay,
Yeah.
okay, sir. Can go ahead.
That is where the NOC architecture today, this specific point, right? This is very complex. Why? Because we get requirements like engineers who have worked on NOC, network of connections. So because it's very complex, because there are many peripherals connected here, and one bus is coming from processor, right? Let us say AHB or AI. To this in here, okay, and then Ethernet, USB, all these directly connected to this bus itself, right? Again, from the bus bar. Further, bridges are used to connect, other peripherals. Even if there could be, if it is AXI, AHB to AHP bridge, then
Yes.
AXI to APB bridge, like this. So now the SOC, complex SOCs will have this. Further, there could be even other, now DSP processing, all that, right? And graphics. Now today, SOCs, if you look at graphics processor, your generic processor, and one more is your DSP for audio, video, and all that. So all these cores are used anyway. Okay, can I move?
Yes, sure.
Sequential circuits. So the moment we think of sequential circuits, right, the processing happens in sequence. The moment you talk about the sequence, now there has to be a reference, right, at the time interval in which the sequence of things happens. Now that time interval is referred by the reference clock. Okay. And the third thing is, now there is a memory, right? We use memory elements in the sequential circuits. The moment it happens in sequence. Now what was the value in the past cycle, right? In the previous time, what was the value, and then now current time, right? That's how all this around this, the sequential circuits are built. And now we use flip-flops to build the register, and then flip-flops to store the value, and then multiple flip-flops in order to build a register. Series of flip-flops we use in order to build a register. Register means what? It's storage, right? A 1-bit flip-flop, one flip-flop can store 1-bit value, right? And series of flip-flops, if you arrange, either 4-bit to form 4-bit register, 8-bit, 16-bit, like this, right? That's how simple ALU your processor take. If you take an example, so there will be simple registers defined: register A, register B, register C, maybe in 8085, 8086. So A, B, C, D, maybe the register names. Each can store maybe 8-bit processors. They will have 8-bit registers. Now, complex this one, if you come to ARM, they are all, 16-bit and 32-bit registers are used, R1 to R15, all right? So that. Now, sequential behavior can also be described using finite state machine, FSM. Okay. Now, in order to describe the sequence, there has to be a way, right? That is through FSM. Now, you saw the APB itself. I have not gone too much into it, but I showed you that there is some idle cycle, there is some setup cycle, there is some access cycle. 3 clock cycles: first clock, second clock, third clock. Now, how do you describe? You can use FSM, simple FSM, in order to represent states. This state, this state, this state. Sequential circuits are triggered by clock edge or pulse, clock pulse. Okay. Combinatorial circuits present outputs, right? On present inputs. Now we will add a feedback, means, right, in order to store the memory, and the previous state can be retrieved, right, from the memory. So this additional thing is added in order to, that constitutes the sequential circuit. So still I take my famous example, right, this clock divider, and in order to represent a sequential circuit, right, and like I explained, so this is NOT gate, and then this is the flip-flop, and the timing and all that I will go step by step here. So is for the sequential circuits. Duty cycle, on time, off time, the complete. This one is called 1 clock period, right? And if you take any device, right, it is driven with a clock, and that clock reference is coming from a crystal, right? And the crystal, and then you will have your own the buffer, and you will connect to the clock. Right? Or fine. Able to hear?
Fine, it's fine.
Is my audio? Yeah, some are saying no audio. That's yeah. Yeah. Okay, so now the clock period, duty cycle, right, and the frequency, right? Now clock frequency is the reciprocal of the clock period. So this is 1 clock period. So on time and off time. Here I have shown duty cycle as 50% duty cycle. So fraction of on time and the off time. So this is 50% on time and 50% off time. This is duty cycle is 50%. On time is equal to off time, right? So simple to understand the clock behavior, right? And how do you generate the clock, right? Example, clock is coming from external source. Now, when you are verifying, you are generating clock from test bench. This forms your test bench actually, right? From your test bench, you generate the clock. So now based on the clock period, right? You generate the clock. That's shown earlier. So whenever only one line, no need of begin and end, clock is initialized to 0. You as reg because anything you assign inside initial and always it has to be reg. And now always clock period by 2, right? That is clock period is 5, means period by 2, 2.5 nanosecond, right? 2.5 time unit is on, it will be on, and another 2.5 units it will be off actually. So this is actually what is the frequency. If I say this, if you take the same values, what is the frequency? Clock period is 5. You tell me that. Now, similarly, you can generate clock in different clock. You just hard code. This is hard coding, right? And then this is what is the frequency here. And now the same thing you can define like this. Always clock is 0, wait for 10, then clock is 1, then wait for 10. So because always it is a reentrant process, right? Once this is over, again it keeps coming. So that way, this is, you can generate the clock like this also, right? So now this is one more way is you can use forever. Forever you can use, and then you can generate the clock. These are the different ways how you can generate clocks from the test bench and then apply DUT clock input, right? How are we doing? You know already. When we instantiate the design, we connect the generated clock to the clock port. Okay. So any questions here? Are you understanding what is the frequency, right? Didn't get here. At least here. Is it tough question? What is the frequency? Yeah. Yeah. So this is 200 megahertz. This is so 100 megahertz and period is 10. So 10 on, 10 off. Total 20. So 20 second is the clock period, then 50 minutes. Okay, so sequential circuits. This is very important concept, right? And you have studied all these basic, flip-flops and the latches, SR latch and all this. I just rushed through. So latches are the basic storage elements, are used for memory design, and they are level triggered. Okay, they are pulse enabled, right? SR latch can be the example, right? You know the truth table and then the gate diagram, right? Also, very specific inputs. It will produce an invalid state. The rest are in the NAND based one, this will be invalid. When NOR based, this will be the invalid. All right, and so where the risk around condition occurs and trying to store both 1 and 0 at the same time, right? Whenever this is, and then this same occurs whenever SR is 0 here. So it's more of theory part. So that's where gated latches. All right. So basically, you are adding one more set of this thing in order to enable, right? And then set and then reset are added, right? These are gated. So now here, how the gated, latch works actually is you look at all the inputs. What is D? D is this. Little bit. One of the example I take. This is D. D is the input. C is the enable. Okay. Now after the a point in time. Then Q here after okay. So the follow that D is changing from 1 to 0, 1 to 0. C is 0, right? Because this is enable. S is 0, then R is 1, right? Then R will be 1. Okay. And so this is how the delays, using enable. Still I am not that. I'm just referring to the to pass input to the output, some delay after assuming here. Here some delay, some delay. What is this delay? This gate delay. Okay. So that is a bit about latches, and how do you model latches? Basically, now look at the two table. Whenever enable is there, right? You pass D to Q. That's what happens here. Else, it will be holding the previous value, right? So this is latch RTL in Verilog. You can represent the tables. Similarly, you go through this right, and then based on the truth table, right, you write this. You write as per this truth table 00011011. So here memory previous value, right, whatever is there, it will be there. When this is 01 case 0, this case is this one. Now 11 is undefined. You can model the flip flops like this, and if you want the test bench, right? Test bench, the clock and the reset are added, and the clock and reset. Now clock generation you can generate in the test, and this clock you have connected here. Reset, right? Yeah, here you can give a stimulus here. Okay, same way with respect to the clock, right? So the flip flops I have modeled here. Okay, so D flip flop, Verilog code, right? And how the output follows the input in the D flip flop. For example, now in this clock, D is 0. D is 0. I come to the timing here setup time, it has missed this one, okay, which will be captured in this cycle, and then D is here. So in this D is 1, in this, right, like this. And the D flip flop, right? Master slave D flip flop you can look at by using this inverter, right? And you latches in order to make this master slave flip flop, right? And similar way, how I analyze the timing waveform, right, with respect to the clock, D and DM, QM, QS, right? All these are analyzed based on the I explained. So here, for example, now here clock, clock pulse, and then here see the inverted one is given, that is CM, right? Now the CM is high here, okay, and now the DM is changing here, D is changing, clock is 1, and in this QM is here because QM is CM is 1, this is 1, this is 1, you're passing here. So like this you can ask with respect to the time, right? Now what is the input and the output? So at the flip-flop level I am showing. So JK flip-flop, right? You know how we construct the JK flip-flop in the truth table. And similarly all truth tables I have. So now JK flip-flop code as per the truth table and test bench, right? So yeah, T flip-flop. What is T flip-flop? T flip-flop is a special case of JK flip-flop where you are tying both J and K to 1, right? So basically now with this input, output toggles every alternative cycle. So that you get, you know, output of the T flip-flop is half of the given clock actually, okay, speed wise. Period is increasing and frequency is divided, frequency divider. It acts as frequency divider. So whatever one clock cycle, it became half clock cycle here. Two clock cycles you need in order to make one clock cycle here, right? That's how the T flip-flop works. Okay, so now this T flip-flop and the modeling and the so this I will push. Yeah, this is of interest. Latch versus flip-flop. What is the difference between a latch and a flip-flop, right? Latch is level triggered, as you saw. Flip-flop is assume this clock or enable behaving like this. T is the input, okay? Q, if it is a latch, what is the value of Q? What is the output value at each stage? What is the value? Let us compare. Changing arbitrarily like this, that's an input. Q latch, you look at whenever enable is there, whenever this is enable is there during this time, whatever is the input pass to the output. Or you see, input is 1 here, output is 1. That's why output is 0, though input is 1 here. Please observe carefully here. And now this complete input, what is changing, is passed to output here. And next, when enable goes 0, now all this is knocked off. No output means output is remaining with the previous value. That's value, right? Whenever it is disabled, right? And then again enable, it passes this to passes during this time, this input to this disable, this is cut off, right? Basically, the output here, the Q output latch goes low here. Okay. Now flip-flop. Flip-flop, unlike this latch, what should happen? It just samples. I don't care what is happening in between. I sample only at this stage. What was the value of D? 1. I set flip-flop output to 1. Now I come here. I saw what is D. It is 0. And then I pull the output to low. Over. I don't care what is happening in between. So that is where most of the time except memories, we prefer flip-flops because the reason that all these transients we call glitches could be changes, right, which may be unwanted, a pulse of different widths and some noises. I want to filter out everything. Only the stable value I want to take and then pass on for reliable, data transfer, right? So that is where flip-flops, are very useful. So if you use latches, it passes it input to the output as is. We don't know whether it is noise or whether it is useful signal. right? And even a small glitch noise can get passed to the output in the case of latches. So that is the difference. So latches and the flip-flops, they are built using gates, and flip-flops are built using latches and made edge triggered. Latches are used made edge triggered for flip-flops. So latches continuously checks inputs and changes the output accordingly. It continuously checks inputs and changes outputs only at the edges of the clock signal. Okay. This is level triggered, edge triggered. Okay. This is sensitive to the pulse. Means what? Throughout the pulse, this latches are sensitive, but this is edge triggered and edge sensitive. So it can be used for modeling memory, and then register, shift registers, frequency dividers all uses this, right? The flip-flop. So in a way, these are synchronous and these are asynchronous. Now, I cannot expect the output to be, synchronous, in the case of latches. So this is very important concept actually. Again, from the interview perspective, as no clock signal, it just as an inheritor clock reference. Okay, so that's how are the storages, the flip-flops we discussed, and the latches we discussed, right? Latches and the flip-flops. Okay, so
Sir,
yeah.
can we move ahead with the state machine? No, we will not have otherwise time. Because of flip-flop and register, basic digital design concepts, I feel like probably be comfortable with these three.
No, and I'll just pass on this.
Because FSM modeling in Verilog
Maybe I will show.
probably will be a very
Yeah.
good for them. Yeah.
Yeah. So what we will do is now maybe we will break for lunch, and then I will explain this simple LFSR design, and I will simulate and then show. Okay, and then further we will move to counters and counters. So I will just through, and I will simulate one or two examples in the sequential circuits. Then state machine will go. Okay.
Okay.
No. Okay. So shall we?
So now you want to break?
Yeah.
Achha.
It's 1 o'clock, right?
Okay. So we'll come back up to 2, right? Sharp 2, because
Yeah.
now it is 5 minutes, so remaining to 1.
Yeah, we will resume.
Okay.
Resume at 2.
Okay, we'll resume at 2, and but then you need 2 hours, right?
Yeah. So 2 to 4 is right. 2 to 4,
Yeah.
I am okay. So if you want me to directly jump to state machine, is fine. So we will discuss about state machine. Fine.
Any participant, if you want to say something, shall we? Because it's your choice, whatever. Okay, we'll jump to state machine. No comments. Okay, we'll break for lunch then. We'll meet at 2 o'clock, right? Okay.